Okay, hi everyone. So in this video, we are going to talk about the third law of thermodynamics, which is really the forgotten law, but it really gives meaning to the second law of thermodynamics. So the third law of thermodynamics says that at absolute zero or 0 Kelvin, the entropy of the system is equal to zero. So to write this in mathematical notation, we say that the entropy at T equals 0 is equal to the Boltzmann constant times the natural log of 1, meaning omega, our number of microstates, equals 1, and that is equal to 0. So at no temperature, the entropy is 0. What does this mean? This means that we need to imagine a perfect crystal. No defects, no missing atoms, and let's pick xenon, a nice ideal gas, and we're going to cool this crystal to absolute zero. This means that there's going to be no thermal energy, so these atoms in the crystal, they cannot move. They are frozen in place. And we also know that every single one of these atoms is the same. And so we cannot distinguish between them. And that means that there is really only one way for us to organize these atoms in a lattice. Now, what do we actually see? As we take a sample of carbon monoxide and we cool it down to very low temperatures and we determine its entropy, we find that the entropy, as we drop temperature, gets low, but it does not go to zero. Instead, we have some residual entropy. And so our question becomes, why does the entropy not go to zero at very low temperatures for a sample of carbon monoxide? Of our graph, that is the baseline of our molar entropy that we see. So in crystalline carbon monoxide, the molecule can be arranged in two ways. And so we can think of this as the black is the carbon, the red is the oxygen. And we can have this with the carbon up or the oxygen up. And so if we start figuring out our number of arrangements, our microstates, the question becomes, how many ways can we take two CO molecules and arrange them? And the answer is 4. And so this means that for 2 molecules, we found, we found that there were 2 squared ways of arrangement. Now, if we have n number of molecules, any number, it turns out that there are 2 to the n number of arrangements of these molecules. Picture. So since there are 2 to the n number of ways, we can plug this in where this is omega, and we can use our S equals K log omega equation. We can rearrange things. So our log rules tell us that we can pull this exponent down in front, giving us n times kb times the natural log of 2. N times kb is equal to r. And so that gives us that the S of the molar entropy of CO, based on this number of arrangements, is 5.8 joules per Kelvin mole. And if we look back at our... Okay, so where is this residual entropy coming from? It turns out that CO has a dipole moment. I know, we keep bringing in all of these gen chem ideas. So we have carbon monoxide, and it has a dipole moment pointing towards the oxygen. And these dipole moments are going to want to order. They're going to want to arrange themselves so that they all point in the same direction in order to reach their global ground state or zero entropy or lowest energy. At very low temperatures, the time scale for reorienting these molecules is much too long for us to observe. We're talking eons. And so this disorder that we see, where some of these dipole moments are pointing down and some of these dipole moments pointing up, this is the residual entropy of carbon monoxide. And so this residual entropy, often from things like orientation, dipole moments, things like that, this residual entropy is what is preventing us from experimentally reaching absolute zero. And so this means that the third law of thermodynamics is still, in a sense, a thought experiment of a perfect crystal with one possible ordering having zero entropy at absolute zero.